Okay, so once again, short and weak, real short, because we've got a quiz on Thursday. Ooh, more than just this. Quiz is chain rule, implicit, also that data stuff, data tables, and related rates. So we better make sure we know how to do related rates problems, because there's a quiz on that on Thursday. Friday's house party half day. Hooray! Wednesday is our memorization quiz. I know it's going to say bid today, but I figured no one would cry if I pushed it to Wednesday. So that's going to be the derivatives, as well as, I think it's called, it says chapter 2, but it should say chapter 3 on it. If you're curious about which one of those memorization sheets I'm referring to, it's the one that has derivatives on the front of it. I think it's the blue one. Yeah, it starts off slope and secant one. I'm just going to say chapter, I'm going to write chapter 3. You could write it as chapter 3. I don't know why it says chapter 2 on why I didn't know. And we do have 2 related rates homework that I'm going to give to you. Now, the related rates homework we're going to to you at the end of class. It's only got like 4 questions on it, okay? And it's literally like, gotta look at that. So I don't even give you the picture for that. Okay, so you're going to need to know how to set it up, and you're going to need to know how to solve, so we need to work on these. Okay, any questions? All right, well, your homework was to read through these and set these up, so I'm not going to grade you on that. It's just you're going to do better and be more aware of what the heck is going on if you did that. So those of you that did a good job. I think this was the first one, right? Conical tank. One of the things that I asked you to do is to set these things up. So I think there was and this is something you have to memorize. It's an equation. What else did I tell you? Equation and picture, whatever. Formula is what I called it. Formula and what else? Picture, formula and picture, I think.
Yep. And then given how and what.
Then there was given rate.
Oh yeah, no, given.
And then find.
Find. And then there's win. Now, these demonstration problems, we're doing the win at multiple times. On your homework problems, I just asked one win. So actually, it's kind of nice. It looks like for our picture, we have something that looks like this, some sort of cone. And we have a water level with a radius, which is a function of time. And we have a height, which is a function of time. Okay? Water is flowing into a cone at 2 cubic centimeters per minute. That sounds like a given rate. 2 cubic centimeters per minute. Did anybody have what that equals? Water's flowing into, so that's the change in what over the change in time? Okay, dr. It's not the change of the radius. The radius is changing. The height is also changing, but this is not.
Oh.
Okay, so you have to think of it. R is a radius.
It's
okay.
dp.
So what does that mean? What would you measure that in? Centimeters. Height is a height. Is a length. You would measure that in centimeters. What type of thing would you measure in cubic centimeters? Volume. So this is the change in volume over change in time. So that's where those units can actually be sort of a clue for us. Then what they want us to find is how fast the water level is rising. Okay, so that's how fast it's going up. Anybody have an idea what that would be? Now, not what the number is, but what's that quantity? What's the symbol for that? How fast the water level is rising. That's the change in
dH over dt.
dH over dt. They want us to find that when it is 5, 10, and 15 centimeters deep. So when h equals 5, dH over dt when h equals 10, and dH over dt when h equals 15. But I didn't actually go back and write my formula. So did anybody have a formula that relates to this picture here?
V equals 1/3 pi r squared times height.
also tell us a little bit of other information. I don't know if it's going to be really helpful, but we'll put it in here anyway. They tell us that this cone has a height of 16 centimeters and a radius of 4 centimeters. So we'll go ahead and label that too. So the whole entire height of the cone is 16, and the whole entire radius is 4 centimeters. So let me ask this question. Is the height of the water always 16 centimeters? No, because we're filling water in. It starts off with 0 height and then it starts to go up, right? What does 16 represent?
The maximum.
Yeah, the maximum height. What about the radius? Is the radius always 4? No. Maximum radius is 4. Down here, the radius is like 2 or something like that, or 1 maybe. Okay. All right, I think that's fine. I think we understand that. Let's go ahead and what was the step 1 was the setup. Do you remember what step 2 was?
Finding the derivative of the formula.
Find the derivative formula. So take the derivative of both sides with respect to time. Okay? So remembering that the volume is changing with respect to time, the radius is changing, and the height is changing. Okay? So here we go. The derivative of volume is just dV over dt equals, now this is one of those formulas that we took the derivative of last week. Okay? So 1/3 is a constant. Pi is a constant. However, r squared is a function. It's a function of time. So when I see this, 1/3 pi r squared times h, I'm thinking, all of that times this, right? So then when we're thinking derivative, we're thinking product rule. So here we go. So the first, 1/3 pi r squared times the derivative of the second. So the derivative of h is just going to be dh over dt. Plus the second, so that's h, times the derivative of the first. Well, the derivative of those constants just are the constants, so 1/3 pi, and then that's going to be 2r times the derivative of the inside, dr over dt. Okay. So, let's see what else we have here. So they're wanting me to find dh over dt. So this is the big question mark, right? That's the thing that I don't know. And here in a minute, what I'm going to do is I'm going to manipulate all of this, turn everything around so that the dh over dt is all by itself. Make sense? But before I do that, let's make sure that I've got enough information, okay? Do I know what dv over dt is?
Yes.
Yep. Do I know what r is?
Yes, you do.
What is the r?
It's 4 centimeters. Oh, that's.
No, 4 is the maximum. It's not going to be
true,
4
isn't it?
centimeters all the time. Let's just hold off on that. Do I know what the height is?
Yes.
I will know in each one of these situations. The height is 5, the height is 10, the height is 15. So I'm going to know what that is. Once again, I don't know about that r. Do I know what dr over dt is? Do I know the rate at which the radius is changing? No, I don't, because that information is not given to me. Okay, let's hold off on that. I am going to show you a trick for finding the r. Okay? Alright, so the trick for finding the r is to actually draw the picture. So, over here I'm going to draw another picture. So when the height is 5, does anybody know the relationship between the height and the radius? Here's a hint. Yeah, they kind of do it. It's well, visually they are at right angles to each other. Okay, mathematically they are the same relationship as 16 is to 4.
Oh, okay.
Okay, and the reason is because they both are triangles. You've got a right triangle right here, and you have a right triangle right here, and they both share this angle right here, which means since they both have that angle and this angle in common, they both have that other angle is in common, which means that they are similar triangles, which means that little h over little r is equivalent to big H, is proportional to big H over big R. Because those triangles are similar, right? Therefore, so I can say 16 over 4, the overall height over the radius is, that ratio is equal to 5 over little r. Chloe, ask me a question. You don't seem to be following.
No, I am not.
You get it now?
Yes.
They're similar triangles, okay? This little triangle is proportional to that big triangle. So I can say big 16 over radius 4 is equal to 5 over little r. So we can run the numbers on that, and we can figure out what r is. I think r is going to equal. We may have a number on that for us. Say again, Jeremy? 1.25. Okay, so I can figure out what the radius is in each one of those situations. No big deal. I can figure out what the radius is. I can figure out what the radius is. I'm kind of want to save us some time here because I'm going to shuffle this whole thing around, find for danger. But I don't know how fast that radius is changing. I do not know dr over dt, and there's no little trick proportion-wise that I can do along that line. Okay, and unfortunately, you can't solve for this one and get an actual number if I don't have numbers everywhere else. Okay, so sad news for us, class. This is a dead end. Okay, this isn't helpful for us.
So you have to have every single thing to plug in?
Well, yeah, I mean, otherwise I'm just going to have dh equals 5 plus dr over dt. And I don't know what dr over dt is. And I actually want a number here, okay? I don't. So what we're going to have to do in this particular problem is go back to our formula, okay? And adjust this formula a little bit, okay? We just found, and what I'm going to do is I'm going to rewrite this formula so that is just in terms of volume and h. I want to get rid of those r's, okay? Because then I can actually get rid of these r's right here and I won't have a dr over dt. So the question is, what's the relationship between r and h? And guess what? We already figured that out. So we found that 16 over 4 is equal to h over r. So therefore, this is 4. H equals 4 times r. Actually, I think something we want to say r equals h over 4. So what I do is I manipulate this formula a little bit so that I'm going to substitute this h over 4 into that r value right here. So I have volume is 1/3 pi times h over 4 squared times h. Still not going to take the derivative yet because I want to solidify all this stuff. So 1/3 pi, that's going to be h squared times an h, so that's going to be an h cubed. And 4 squared is 16. So, making this even more simple, the volume is 1 over 3 times 16 is 48 pi h cubed. So far so good? Now let's take the derivative. So dv over dt equals, we'll pop down this 3 at the same time. I'm going to write 1 over 48 times pi times h, and then 1 over 48 times pi times 3 times h squared times the derivative of the inside, so dh over dt. That 3 is going to cancel out with that 48 and have a 16 right there. So I have dv over dt equals pi over 16 h squared dh over dt. If I solve for dh over dt, I'm going to get multiply both sides by 16, so I have 16 dv over dt, and then divide by pi h squared. All right, let's see if we're right. So dh over dt, so this is our formula. I'll now apply it to our 3 different situations. So 16 times 2 divided by pi times 5 squared. When the height is 10, we would have 16 times 2 divided by pi times 10 squared. And when the height is 15, 16 times 2 divided by pi times 15 squared. I'm going to need numbers on each one of these, as well as someone to verify them. Go ahead and set that up while I take minutes. All right, I need some numbers here, folks. 0.407. And what would the units on that be?
Centimeters per second.
Centimeters per minute. All right, keep going. And
0.45.
so, Rosa, what does that tell you about how fast the height is changing?
It's getting slower.
It is getting slower. Does that kind of match what we saw in the picture? All right. Let's see if we did everything right here. So for 5, when the height is 5, we had 0.407, which is exactly what we had right there. 0.102. Feeling pretty good about this. And 0.045. All right. It's nice they actually included a graph for us here showing that the rate actually is almost infinite, right? When you first started filling it in, the height increases, really quickly. And but then as you get the height gets closer and closer to the top, then the rate gets slower and slower, closer to 0. If anybody's ever filled up like something like a swimming pool or something like that has lesser, that's somewhat conical and kind of gets wider or whatever, you can spend, you start filling up and you're like bathtubs kind of do this, because bathtubs also kind of tend to be a little bit narrower at the base. You fill it up and it's like, oh yeah, great, look how fast it's filling up. It's gonna fill the rest of the thing up, no problem, really quickly. But then like, you wait like a minute or two and it kind of goes up a couple inches. And you're like, all right. Then you're like, wait a couple more minutes and it's only gone up like just like the smallest amount. And you're like, what in the world is going on with this? And the answer is because there's going up from 1 inch from here to here is not very much water, but going up 1 inch from here to here is a whole lot of volume of water. It's going to take more time. Let's fill it up. I actually remembered this particular problem very well when I was in high school because of this annoyance right here. And I was like, oh, and I could never remember what this was all about, but it's similar triangles. It's the height over the radius equals the height over the radius. So, anyway, now you know. What's up next? Lamp post. Oh yeah, this one where the guy's walking, right? So, formula and picture, given rate, find, and when. So, y'all familiarize yourself with that over the weekend. What kind of picture do y'all have?
There are two triangles.
Yep. Something kind of like that.
Mm-hmm.
We know that this one's 15 feet. We know that that one's 6 feet. A man 6 feet walks away from a lamppost at 5 feet per second. How fast is the shadow lengthening and how fast is the shadow tip moving? Okay. We're going to need to put some variables on here. Alright? It says how fast is his shadow lengthening. Seems to me we need to have some sort of this part right here is going to be a shadow. Do you want to use S or X or S for shadow? Okay, that seems to make sense there. Anybody put any other numbers anywhere, terms? And we're going to need some formulas here probably. Okay, well we'll hold off on that. What about this? It says he walks away from a lamppost at 5 feet per second. So y'all probably have 5 feet per second on there, right? But what do you have on the other side of the equation?
Distance from the lamppost.
Distance from the lamppost per time, right? Okay. But if we're going to put distance from lamppost, then we're going to need some sort of variable there. Let's call that x. So x equals 5 feet per second? dx over dt. Yeah, there we go. So dx over dt equals 5 feet per second. What do they want us to find? Yeah, ds over dt. They don't, and then they actually want to do, then this question, how fast is the shadow's tip moving? Which, that's going to be, if we, this is the tip and how fast it's moving on here. That actually is, think of, we'll call this whole thing y. We're talking about how fast it's moving. It's going to be, how fast is it from that spot right there? I'll go ahead and show you guys if you start to walk. There it is. We're figuring out how fast is that moving, far away from the lamppost. Not how fast, not necessarily how quickly is it moving it away from him. That's ds over dt. But how fast is that tip moving away from the lamppost? So that's y. We'll figure. I'll put that here in green. They actually have 5 different times that they have here at time 1, 2, 3, 4, and 5. So I guess we could figure that out. I don't even know. At time t equals 1, I guess. So when ds over dt when t equals 1, when t equals 2, t equals 3, t equals 4, t equals 5. You might need to go with another sheet of paper on this one. I don't know. We'll worry about why is tip moving in a little bit. Well, right now we should figure out how fast is that shadow moving. So we need a formula here, folks. Any ideas? Yeah, I understand. You want to go Pythagorean, but we don't know anything about the hypotenuse. But I am seeing at least 2 triangles here, kind of like the last one, okay? The temptation might be to say that 15 over x equals 6 over s, but we don't necessarily have a rule for that, right? Because but we do have a rule for, for saying like that this part is proportional, this part is that part is proportional to that part. But we can talk about the large triangle and the small triangle. We can say that the large triangle, 15 over
Y.
x plus s, or y, right, is proportional to 6 over s. So large triangle leg over leg is equal to small triangle leg over leg. Okay, and they give us when x equals 5, or sorry, dx over dt is 5 feet per second. I don't really care for this way. I don't know about y'all, but I'm going to multiply this out because everything on one side. So 15s equals 6x plus 6s. So subtracting 6s from both sides, so we have 9s equals 6x. That's fine. I think we've got plenty of stuff to go on. So after we kind of have a good setup, what's step 2? With respect to time, right? So this would be 9 ds over dt equals 6 dx over dt. So then just divide both sides by 9, we get ds over dt equals 6 divided by 9, so that's going to be 2 over 3, 2/3 times dx over dt. That's crazy. What's dx over dt? 5. So you're telling me, hold on, so ds over dt equals 10/3, so 3.33. Dx over dt was feet per second, right? So this, according to this, the shadow, right, the length of the shadow is changing at a rate of 3.3333 feet per second. Okay? Now that's different from the previous ones because in our previous problems, our rate, there was more to this right here than just a number, right? There's normally, it depended on when the height was here, when the height was here, when the height was here, or it depended on the radius. Do you see what I'm saying? Like, this was a formula that we never had a situation where this was a specific number, okay? According to this, his shadow is moving away from him 3.3 feet per second all the time. at time 1, at time 2, at time 3, at time 4, and at time 5.
And that's not for all of them?
So it's, say it again?
That's what it is for all of them?
Well, I mean, yeah, because, I mean, look, when time equals 1, do you see time in this formula? I don't see anything in this formula. It's just 3.3. It's 3 1/3. 3.333 feet per second when he's 1 foot away, when he's 2 feet away. It's
So, is the reason why it appears to go like to be moving faster? Is that just because he's walking along with it? Does that have something to do with that?
yeah. Let's look and see what's going on here. So
Oh, okay.
look at that. Look at the shadow length. Does it look like it's moving farther away from him?
Yeah.
I mean, it's moving
but
at a faster
constant
rate.
Yeah, it doesn't look.
It looks pretty constant.
Yeah.
Now that
At
we
the
look
very
at it.
beginning, it's hard to tell. At the very.
Yeah, but I mean, just think of,
Yeah, if like he wasn't moving, it would just look like it's moving away from him.
Right. Now, here's a question. What's the overall speed of the tip of the shadow? We know that it's traveling 3.3 feet away from him every second.
So it's gonna be that plus however fast he's traveling away.
Exactly. And how fast is he traveling?
5 feet per second.
So how fast is the tip of the shadow traveling?
8.33.
Yeah.
Oh wow.
Y'all catch that? It's moving away from him at roughly 3 feet per second. He's moving away from the lamppost at roughly 5 feet per second. So the tip of the shadow must be moving 3 feet per second plus 5 feet per second. Yep, 8.
Wow.
So, kind of neat to see something like that.
Mm-hmm.
Yep, they're all the same on that one.
Wow.
Show the key idea. The man's height over the lamp's height is. Okay. Searchlight. Whenever I look at this problem with the stealth fighter here flying over, I always tell the story about the first Persian Gulf War. Y'all know the United States, we've had two Gulf Wars. I don't know if you knew that.
No.
If you're American, if you're juniors, well, you are seniors now. So you learned all about American history in the 90s and beyond. So when I was growing up, so in the early 90s, Saddam Hussein, president of Iraq, decided that he was going to take over Kuwait, which is a little tiny small country just kind of southeast of him. He's like, I'm just gonna invade them. I've got like the 3rd largest army in the world and I want their oil. So he literally just went in and took over the country. And everyone else is like, you can't do that. You can't just like conquest another country, a sovereign nation, you know? And so the United States and several other countries, Saudi Arabia, I mean there's like dozens and dozens of other countries, we basically formed a big alliance and we kicked him out of Kuwait. And we also kind of went a little bit into Iraq quite extensively, and we just smashed him. Smashed his army. Everybody did. And they're pretty good troops. And he had some I mean, it was like the 3rd, 4th, 5th, something. I don't know, maybe it's the 5th largest military. I don't know. Anyway, it was significant. And it was like a major ground battle. But the first part of that whole war was this was the time we were able to use our stealth fighters, our stealth bombers. Okay, and, I mean people knew that they existed or whatever, but this is the first time that we utilized them. And what happened is we used them to knock out the electrical and communications systems in Baghdad, Baghdad is like in the middle of Iraq. Okay, what's really crazy about the stealth fighters is that they never land on anywhere except U.S. soil. So they will take off from like some Air Force base in Louisiana, and they will fly around the world, refueling at different locations, drop their bombs, and then turn around and fly back and land in the United States. They will, like, we won't land at our bases in Germany. They won't land at, you know, our friendly bases in England or anywhere else. They will only land on American soil. So that's pretty cool, I think. Anyway,
They were
They just
refueled
refuel them in the air.
they refuel them in the air. Yeah, they have a huge tanker that goes in front of them, and then
Oh.
they like lower the hoses, and the hoses like get connected to the front of it, and then they send the jet fuel through, and they say, all right, we got it, all right, detach, and sends a little signal, it detaches, and then it pulls the
So
like front of
cool.
them. So they have to match airspeed and all kinds of stuff. It's a pretty
Pump gas though. You gotta turn your car off and pump gas though.
yeah, but you don't actually have to, but most people do, yeah. But they get the jets flying around, flying up there in the air. And they do that a couple times, or however many times it takes to refuel. I don't know the range of it. Anyway, so so here's the thing. So CNN, being CNN, they've got news correspondents everywhere. So they had people in their CNN Baghdad, right? And they're in kind of outside the edge of the city, and they know that these bombers are coming in because they're dropping bombs on the electrical plant and the power subsystem, you know, location, stuff like that to knock out the power and everything. And so there's explosions and stuff like that going on. But the Iraqis cannot, they can't see them because it's night. But their radar can't see them because the radar signature that these things have looks like a bird. Okay, it reflects the radar waves and stuff like that, and scatters it. And so that's why they're called stealth, because they're invisible to radar.
Mm-hmm.
You can't see it. You can't lock onto it with a surface-to-air missile. You can't do anything with it. So the Iraqi guys, not only do they have like missiles, but they also just have good old-fashioned anti-aircraft guns, where they just like kind of shoot up, you know, they shoot these shells, like these, you know, bullets up in the air. But if you've ever seen them, every like 5th or 6th round has a little bit of phosphorus inside of it, so that when you shoot it, it kind of like glows in the dark as it's going up, and so it's called tracer fire. So there's like, it's shooting up there, and then you can actually see where you're shooting, but they don't know where to fire. So they're literally just going, they're just like randomly spraying the skies above Baghdad, hoping that they will hit one of these stealth fighters. Okay, and so these stealth fighters are coming in, and the pilots kind of tell the story. They're like, we're going in, and it's like a World War II type scene where the Germans are like shooting their anti-aircraft, you know, shells are going up, and then they do little explosions, and it's like, have you ever seen like the old World War II videos?
Yeah.
And like that's what it felt like, and then you kind of see the spray going on there. Would you like to see a video of that?
Yes.
Okay, all right, of course you would. We might not do calculus, but we'll go ahead and.
So if one of the shells had actually hit the stealth fighter,
yeah,
would that have been
But
like
we the
bad?
almost have the USA, the almost have those planes.
Oh yeah, that's true. What other country have those types of
Still.
stealth? Probably like.
Ten stealth bombers were just minutes away from downtown Baghdad. The stealth was designed to be invisible to radar,